A very good morning and Happy New Year to everyone. Yeah. So today is my great pleasure to introduce Professor Vanessa, a chair and a professor of human media interaction from University of Twente. Yeah. Okay. So as you can see, the title of the talk is Social AI of People and Robotics, and that might be why we attract so many of you here. Okay. Professor Vanessa Evers, she did his study. Okay, let me see. Yeah. She's also a vice dean of research for the Faculty of Electronic Engineering and also the Mathematics and Computer Science. And she's also the scientific director and the founder of Design Life, a center for multidisciplinary project and the society impact based on the science to design for society. Yeah. So she studied information system at University of Amsterdam, business information science at University of New South Wales, Sydney, and she has a PhD from the Open University, UK. So she has worked for the Boston Consulting Group and has been a scholar at Stanford University and also a part-time professorship at the University of Delft. So her work sits besides in between the interaction of computer science, psychology, design, philosophy, and electronic engineering. Okay? And the focus on human interactions with artificial intelligence system, as well as the cultural aspects of human-computer interaction. So her work covers design of artificial intelligence systems that are able to interpret human social behaviors and respond to people in a socially acceptable ways, as well as the evaluation of the impact of such system. And she's a frequently public speaker at various of the international conference, as well as the World Economic Forum at Davos. So without further delay, let's welcome Professor Vanessa Evers to give the talk.
Thank you, Professor, for this very kind introduction. And thank you for coming. I understand the classes have not really started yet, and to see you here is really nice. I look forward to speaking with you about this topic. Please feel free to raise an issue if you have something to add or have a question around it. Otherwise, at the end, we can also have a discussion. Well, Professor, you were so kind to tell my background already. So really, this slide is not really necessary anymore. Maybe something I would like to highlight is that I am a woman who works in robotics. And there are not many women that work in robotics. So normally when I give a talk like this, the room is full of men. And they think, why is she there talking about robots? So I have this, what I kind of call my kind of gloating sheet, which has all these logos of, say, Stanford, and that makes them feel, all right, we will listen. But of course here, that is totally not necessary. Maybe to highlight this, I studied at the University of New South Wales in Sydney, and I did a master's degree where I looked at cultural aspects of how people interact with technology, cross-cultural aspects. And I've learned how difficult it is to understand how someone's culture influences the way that they behave and respond to technology. Similarly, during my PhD degree, which I did with Jenny Priest, who is a very famous human-computer interaction professor. At the time, she was at the Open University. I had looked at kind of cultural aspects of technology. And then, of course, technology started to be able to adapt itself. So I started to look at adaptive technology, intelligent technology, and slowly rolled into robotics and intelligent technology in general. Can you hear me, or should I put this a little louder? In the back, it's good. Thank you. Okay, I wanted to show you my research team, well, part of my research team, because they never seem to all be there on the day that we take a photo. But basically, what I want to show you is that it's quite a diverse team, not just in gender and in nationality, but also in their background. It's slightly unusual for a research team to have backgrounds in different disciplines. But it's because when you want to develop robotic solutions to problems, you hardly cannot have a very kind of focused view. If you are the best group in robot hands, it will be very difficult to design a holistic solution for a problem. And what we would like to do is address problems that exist in society and develop holistic, aware systems that are able to deal with those problems. So some of the people in my group are psychologists, or they might be designers, they might have a electrical engineering background, of course, an AI background. It is very mixed in general. Here are some of the platforms that we either helped develop or developed within our system, within our group, and I will tell you a little bit more about them. What they have in common is that they operate in highly social environments. So they're not in a cage, in a factory, far away from people. They are operating and collaborating very interactively with people. And I think we can all see that the world is developing that way. Elon Musk quite recently said, well, we made a mistake with the Tesla factories. We designed all the people out. And in a way, we designed all the flexibility out, because no one can just move in, take a piece of paper and walk out. You have to call to France, to the team that has to fly in with a helicopter to fix the robot. The whole factory has to be shut down. So they really are coming back from that idea of designing people out of that loop, and that the intense collaboration between this intelligent technology and humans is something to address. I've been working in this field for 15 years and I was very unpopular. But now recently I am very popular. I think because people are coming to see this is important. So because we are a group with a very diverse background, we kind of cover a range of topics in a way. So we want to achieve something that I call social artificial intelligence. Machine intelligence that is focused on social awareness. That means that we need to be able to automatically interpret human behavior. It also means that we need to be able to sustain an ongoing dialogue, probably multimodal. And it means that machines need to be able to reason about the interaction and extract meaning out of the interaction with the humans in the environment. And I would like to tell you today about where we are in that process, what we have learned in the time that we've been working on this, and what we hope to achieve next. So let me start by explaining the background and how I got to this topic to you. This is how we know robots. They work very well in chessboard-like environments, extremely structured environments, where it's very clear, there are clear rules what to do and when to do something. There are arrows on the floor where the humans can walk, but it's a robot's world. And these protocolized environments are traditionally very robot favorable. However, robots are not obvious solutions to all of these problems. They are heavy, fragile, expensive. They are single-function devices that cannot switch between context. You can see here how difficult robots find it to switch context. The robots that you see here of the DARPA challenge. Robots are trained through machine learning. So they learn to choose actions based on detected features or cues. It's a great movie. So you could say there's really no knowledge. And looking at this robot, poor robot laying there, it really feels like there is no knowledge. But the knowledge representation is in the form of code, the algorithm itself. And I don't have to tell you, but sharing algorithms, sharing code is extremely inefficient. You can only have that through software updates or a Git push or pull for the more technical people in the room. So this mostly happens between robots of the same type. So that means that this exchange mostly only happens between research groups that are tightly working together within research projects. So this learning is highly inefficient. It's not scalable at all. And there are a lot of problems around machine learning that we need to solve before robots will be able to switch contexts like this, especially seamlessly, which is what we need. So I wanted to find inspiration for cross-context learning, and I started to look at how people learn. So this is a photo of myself. I am the baby. And I wanted to show you how I learned. So the photo is here with my grandmother, Tuminem. She is from Indonesia. She grew up in an inland tribe, in an inland tribe in Indonesia. My grandmother, Margaret, she was the station master's daughter in Surabaya. And my mother, Ine, who was a bookstore keeper in the Netherlands. That's the best description. In the social environment here, I learned to smile. And I learned to respond to people. And I learned to hold objects and make sounds. And I learned this socially, like all of you have. You've all learned socially how to behave. And it's interesting how that works. Your environment shapes you. When I was 2, I moved to Africa, to Nigeria, with my parents, where my father worked to build an airport. And so why am I showing you my family album? I wanted to tell you about social learning. This social learning is something that I want to explain to you how I have automated that into computers. So we learn from our social environment. We pick up cues, and we learn how to respond to those cues. So how do we do that? And here you can see the mother-infant relationship, or here. And this mother-infant relationship needs to be loving. It needs to be nurturing. For humans, as well as many animals, especially great apes, for instance, chimpanzees, to develop into a very fully functioning adult. If there's no love or nurturing at the early stages, there's no possibility to become a fully functioning adult. This is extremely important. However, for people, the mother-infant relationship or parent-infant relationship, I have no, I have no opinion about that. It's very different from, for instance, the great apes. So for us, it's characterized by physical separation. And we hold our children, of course, but we put them in a little chair and we put them in a stroller, and we look at our children because of this physical separation. Also, human infants have a very early, stable, supine posture. They can hold up their head and their backs quite soon, much sooner than, for instance, chimpanzees. And because of this, it enables us to have face-to-face communication with our children. We have vocal exchange, we show manual gestures, and demonstrate object manipulation. And this process is called social referencing. It's a very human process, inherently human process, where the infant takes cues from the people in its environment about which emotions and which actions in which context are appropriate. So infants observe the behavior of others, and through social referencing and through our active teaching, we teach each other concepts extremely efficiently, very scalable. So we love seeing photos of baby chimpanzees like this because it's so recognizable. But really, this is how baby chimpanzees spend most of their time. Or this is how they spend most of their time. There are several critical differences between the two species. Chimpanzees lack the social referencing abilities that are so human. And chimpanzees seldom engage in active teaching. So social referencing and active teaching are important concepts if we want to engage in social learning. So I work with a Japanese primate researcher. His name is Tetsuro Matsuzawa. If you are interested in this, you have to find out about his work. It's really extremely fascinating. And he argues that the mind and culture in humans is fundamentally different, for instance, from apes, because of this manner of raising our young children, because it is so characterized by social learning. And his position is, his theory is, that this aspect of human child raising might be linked to the development of empathy, altruism, understanding others' minds, and enculturation, to be able to become a culture, because we are teaching each other habits and traditions. There is one chimpanzee group in Matsuzawa's research environment. It's in Africa. I think it was in Rwanda, but I'm not sure anymore. And that is the only group where he found that children learn something. And basically, it's a group that uses a rock to open a nut. And it takes a chimpanzee child 7 years to learn to open a rock because there is no real learning. The chimpanzee parents don't engage in active teaching, and the chimpanzee child does not engage in social referencing. So they kind of pick it up after 7 years of total exposure, of days full of rock-hitting nuts. So he argues that because of this lack of social referencing and lack of active teaching, there is no enculturation in, for instance, great apes. We shouldn't talk about culture when we talk about apes. Whereas, of course, we hang on culture. So of the great apes, well, you could speculate about this, but let me say, only people undergo this process of enculturation, of creating a culture together, of having cultural learning, social learning. And it's the medium of delivery is this social referencing. Okay, so I had the great fortune to work together with a famous philosopher called Dennett. And as part of a Dutch TV program, I was allowed to interview him about this exact topic. And I really loved his answer. It's a couple of minutes, so I'm going to ask you to sit through it, but he tells it so much better than I could tell you.
Robots made of robots, made of robots, made of robots, made of robots.
He says we are robots made of robots.
If you look at a single cell, a neuron or an astrocyte, that cell is a sort of autonomous robot of itself. And if you look inside the cell, you find even more robotic parts moving around. Motor proteins are very clearly, they're not even alive, they're just proteins, but there they are marching around inside a cell, carrying goods, creating little highways, and then walking along the highways and doing all the transport that's needed inside a cell. Those are robots for sure. They're nano-robots. Not a single one of those knows who you are or cares. But how does the mind pop out? That's the question that concerns me the most. How in the world do you ever get that out of 200 billion clueless little robots? And the answer, I think, is only because of enculturation, only through culture. It's the evolution of culture that makes thousands of thinking tools, thousands of informational devices that are all designed, ready to use, that get installed in our brains, roughly the way you install an app on your smartphone. And these give a human brain all these other powers. They work together and they create functional architectural levels which simply don't and can't exist in the mind of even the chimpanzee. So it's the software, the levels and levels of software that are imposed on the underlying hardware of the brain that do all the work that make the consciousness. That's my theory. It's controversial, it's speculative, but I have, I think, some pretty good arguments for it.
Okay, I found this very inspiring. A humanities professor and the biology professor who have such inspiring views that together could give me an idea of how to approach this subject of machine learning. So, just to recap this concept of acculturation, to be able to learn socially from others is really important. And it's a really efficient way to transfer knowledge. Maybe machines could try to have this way of transferring knowledge. Having relationships and the ability to learn from those relationships will allow the learning of skills efficiently. And it may even explain the way our brains work. That might influence artificial intelligence research again. So, I want to convince you that our social environment makes us, that our social environment tells us how to behave. All of you chose a seat to sit in today, and all of you have your arms and your legs at a position that is socially normative and that is reasonable to do in this context. These social norms by which we move, we say hello, we talk, we work, it makes us feel and know what is right. We instinctively know what is right and what is wrong. So social norms are norms that determine our behavior. And they were taught to us by social referencing. We don't learn them explicitly at school. So here's an example of what happens when you don't adhere to social norms. You know this is wrong. And when we do not adhere to the social values around us, the consequences are disastrous. People feel threatened. They might become aggressive. It's because you are not fitting into the social environment. This is videotaped at Schiphol Airport. It's crazy to think that every day we use and we make technology that is like this man here. It does not take into account our social norms. If we want technology to be successful, if we want people to use our technology, it must have and comply to social norms. He's not making friends. And I think all of us can mention technology that we use every day that is like this person. It is rude, interruptive, it doesn't take into account my needs. And that is really something that we want to establish, to find a way for machines to infer the socially normative environment and to be able to act accordingly to that. So I adapted this. It's very roughly based on Professor Cynthia Brazil's model at MIT. Basically, you have to generate behavior, you have to detect the environment, and you have to do an interpretation layer. And I feel that where we are now is this, what we are good at is this incidental interaction. There's a robot in the hallway, it sees you, and it goes to the side so that you can pass. And now we are kind of struggling with this real-time dialogue. How to have some kind of meaningful dialogue, for instance, with Google Home or with Alexa. It works in context, and we are working on it very hard to be able to have that dialogue extended and more meaningful. Towards something like social interpretation, to be able to interpret and see the social behavior in people. It's being done. People are looking at lie detectors, for instance, for ages. But maybe you want to interpret the social environment, and I want to tell you more about that today. Towards social referencing, which I explained in the beginning, to observe the social environment around you, pick out the cues, and learn from them. Towards something that, hopefully is something like social machine learning. Intuitive learning from observing the social environment, multiple people in there. Okay, so let me tell you how that works, kind of a 101, because not everybody here has a computer science background. That is correct assumption. Yes? Okay, great. Then I will keep going like this. So the first step is maybe can we understand automatically kind of basic behaviors like emotions. And I'm sure a lot of you know about systems that are able to detect emotions. This is Maya Pantic. She's also affiliated to my group, and part-time she's at Imperial College in London. And what she's really great at is using computer vision to detect facial features. In this case, valence and arousal, things like happiness, sadness, etc. And her algorithms are so good that they work in crazy outdoor conditions, where the light dapples through the trees. A computer could never see a face, but the algorithms are getting so good that we can start using them outside of the lab. So you're getting technology that can recognize basic human emotions. And I realize there are many ethical questions about almost any slide that I will show you today. Anything I talk to, and I'm very happy to have that discussion with you after my talk. But at the moment, I will just tell you the technological aspects around it and tell you that it's very important to have these ethical discussions, and that I hope we can have them today as well.
What are you plotting?
Sorry?
What is the plot?
Oh, the plot is valence and arousal. So valence is the positive negativity of the emotion, and arousal is the intensity of the emotion, high arousal or low arousal. And they are a very good indicator of the basic 5 emotions of happiness, sadness, disgust, etc. Yes. Does that answer your question? Okay, great. So, machines can kind of get this basic stuff. But what about more complex social situations? So we thought about the most complex social situation at all. I will play it for you now. And it is speed dating. We thought, okay, if we can get a machine to predict whether people have a match in speed dating, that's a pretty difficult social situation. Would you agree? Again, it's not uncontroversial. I'm happy to have the ethical discussion with you later, but let me get through how we set up this experiment first. So what we did, was we set up an experiment around speed dating. We invited many people to speed date, of course, explained to them the setting and the confidentiality of their data, etc. I can tell you more about that, or you can read the paper about it. And then we set up as many sensors as we could. We measured everything we could. So we have laser rangefinders there, we have lapel microphones, directional microphones, videos from all sorts, markers on floors, anything to be able to detect features of what might indicate behavior. Then at the end, of course, we had the matches. We knew which people had a match during their speed date. We fed all of that to the computer and then asked the computer what is predictive of a match. So what feature would predict that people like each other? And the computer came back with one singular feature. So I am asking a speed dating expert in the room. Is there anybody here who feels comfortable to tell me about what might predict people to like each other for speed dates? Yes, our expert.
Distance.
Distance, very good, very good. Close, close, yes? Sorry? I'm sorry, I'm slightly deaf. Appreciating each other. Yeah. Yes. So you mean like smiling at each other, being nice to each other? Oh, thank you. Thank you. I understand. So what was said voice-wise, we thought the same, the content of the speech. So we spent a lot of resources in analyzing the content of the speech, and it did nothing. So that was a shame. Another thing that I thought of was eye gaze, stare in each other's eyes. Well, I'm obviously not very successful because that did nothing either. Let me tell you what it was. It was very close to distance. It was actually the variation in the distance. Let me show this video again. If we had done this experiment sitting down, nothing would have come out. The variation in the distance, so not how far or how close people were, but the more they varied their distance towards each other, the higher the likelihood that they would be a match. It's the most predictive feature. So, I have now empowered you greatly. I need you to use this scientific wisdom carefully. And if you ever meet the love of your life because of me, I want to know about it. Okay, so computers can analyze social situations in a way. It's something we can do. So then we started developing systems.
Et si vous visitiez l'Alcazar de
Let me see
Séville,
if I can turn this down in
Suivez-moi,
French.
s'il vous plaît.
avec un robot. Frog est le premier droïde
What
guide
is fun about this
touristique.
is a French news channel
Fasciné,
that covered the robot, but they
amusé,
dubbed the robot, so it
intrigué,
starts to speak
sur
French,
son
but it
passage,
doesn't speak
il
French,
ne laisse pas les
which is
visiteurs
funny.
indifférents.
But let me tell you
À
about
présent, nous
this.
passons à l'étape suivante.
C'est sympa. On se croirait dans Star
I
Wars.
can't turn it down completely,
Frog
but
choisit lui-même son
I'll talk
itinéraire
over it
et
if
les
that's okay.
thématiques abordées au cours de la
So what we
visite.
wanted to do was understand what will happen in society when robot services start entering everyday life.
Bienvenue dans la
So we
phase
want an
des-
example of a mini society where robot services could be deployed for us to analyze what effect that would have on the people that work there and the people that live there. So this is the Royal Alcazar in Sevilla in Spain. We also had a robot in the Lisbon Zoo, and what it functioned as a tour guide. So it would recognize when there were people there, it would go up to them, ask them if they wanted a small tour, and it would detect their interest as they were listening to its information. It used augmented reality to, for instance, show on the display, on top of the scene behind, historical events, or what rooms might have looked like in the past. And it would gauge the interest of people, and here's a little video of how that went. And then adapt the content that it would show depending on the interest that people in the environment had. This is from the point of view of the robot. So in order to do that, of course, there were many different technical and design and psychological challenges for us to overcome. One of them was pedestrian detection. To be able to navigate an environment where there are many people, I don't have to tell you, I mean, you guys are so advanced on autonomous vehicles. I don't have to tell you the challenge of navigating populated environments. And what I wanted to show you is that this kind of almost frivolous robot a lot of people from the public say, well, when is this robot going to be made available? It's like, well, it doesn't quite work like that. It's not like you buy this robot and you stick it in your zoo or something. It's more that science comes out of these projects. So one of the things that came out is that this algorithm that we developed for pedestrian detection went into the new Mercedes because it was so good at recognizing very different people that it was a nice algorithm. So it lands into the market, it lands in society, but often in modules rather than that whole concept that you are developing together. I want to show you the next step that came out of this study, which is that once we are able to detect people, understand their interest, are able to gauge what they need, what would be nice is to predict the future. So of course, the next step in our work in autonomous cars is to start thinking about what people are to each other. So if we know, for instance, there's a family on the sidewalk, father, a mother, a couple of children, or whatever constellation there is, and one of the children starts crossing the road, the likelihood that the others will cross the road goes up. So the car can start having multiple universes of the future in its head. And as soon as one of these universes starts to become true, it will know what happened, so it can respond much quicker than we could ever respond. This video has nothing to do with my talk, but it is so fun, I wanted to show you. Okay, so I was inspired by the Merlion here. I was like, did he see a sea lion? And that's why he called it a lion, and that's how you end up with a Merlion. But this is my story about sea lion. So we walk around with these robots at the zoo, and I want to explain to you how even animals see something in robots. These animals are always in the back. They don't care about people. They don't care about the little cars. But when we walked around doing our research with the robot, all the animals came to the front, started checking it out. There was something weird about this robot. So we are creating something new in the world. We are creating a new type of agent that not only affects humans, it affects really the entire world. And that's really something we need to work together on. It'll be interesting to work with biologists, work with people who know about flora and fauna to figure out how all these elements can come together. Okay, my second example is the Dispenser Robot. Oh, let me turn this down.
Spencer. His job is...
Down. Okay, let me talk over it just in the interest of time. So the Dispenser Robot was developed, KLM is a Dutch airline, and they said, we want to offer services to people who have just recently come into money. They start traveling, but they are not used to how to travel very much. So we want to offer extra services in their language, but we can't have airport personnel at every gate with all the languages. So what about offering them language with a mobile kiosk, more or less? So we said, all right, that means you have to have a robot that can autonomously navigate Schiphol Airport, go to a gate, be assigned a group, or that people take that group and then take that robot and it brings them to their desired gate or to a transfer area, or maybe there's a gate change and they need to move and it needs to happen fast, so the robot has to run with them. We thought, this is going to be very difficult to realize. So we said, okay, let's start by investigating this. And this is kind of the general process that we go through. First, to observe the environment. What is happening there? What are the norms there? What kind of behaviors do we see? How do people queue? How do you negotiate a queue? When there's a queue, how do you cut through? That's very difficult to set up. What kind of events would a robot have to deal with? Then we start teaching the robot through machine learning. So we give robots many examples. Here are people walking together. Here are people walking together with luggage. And the robots start to learn what happens, what the dynamics are of groups, what happens when a person leaves the group, what happens when a person joins the group, what happens when a group suddenly gets switched with another group, and how to deal with that. We put all that in the computer's brain, so to say, and then develop models. Models of what? This is kind of the airport corridor, of what that would look like. So the robot would evaluate the stream of pedestrians, and then, of course, map its route through there and adapt it as it goes and meets things. Here's another kind of view from the robot's perspective, what that would look like. As it's doing that, it is reasoning about what people are to each other. Might they be colleagues? Might they be a family? Some things you can find out. Stewards and stewardesses from the same airline kind of dress the same, so that's easier for the robot to see. Families are sometimes easier to see. But through learning from examples over time, it learns to deal with the variety so that you don't have a biased algorithm. You can very quickly have a biased algorithm. Yes, please.
Just a question. Is it generalized algorithm where it looks at classes of people and assume that they will move together, or does it have different classifications for different types of groups?
Well, we tried different things. The algorithm you just saw has different classifications for different types of groups. Yes. May not always be appropriate, but yeah. Here you can see what that looks like from the perspective of a robot. So there's kind of the view top-down in Schiphol Airport near the Starbucks. I don't know if you've ever been there, or you've already been to the gates. Basically, there are a few people there. It puts a frame around that. And when this kind of social intelligent algorithm isn't working, it looks at these people, sees that the space is large enough to traverse, and it plans its route accordingly. But actually, when we turn on that algorithm, it starts to reason about what these people are to each other. Maybe their emotions seem to be more dynamically engaged. Maybe their noses are pointed towards each other. There are some aspects that this algorithm takes on and sees, okay, these people actually belong together. And it makes a route around them. And what actually was happening, that person was making a photo of the two other people. So it actually photobombed, which is not very socially normative. But, we are struggling to get there. Okay. Here's another example. I don't know how many of you have children. I have children. I can tell you they make a mess, especially with Lego. And there's nothing worse than walking around bare feet and stand on a block of Lego. So I thought, if I do one thing in my life, I'm going to make a robot that tidies up the room. And my colleague, who's an ethics professor, said, well, that is just not right. Because children have to learn how to tidy and sort and then deal with structure. I was like, oh, okay. So we said, oh, what about a robot that is able to deal with clutter? And the children invest in the robot because it can learn from them about clutter. So it's like a two-way thing. And it's a computer vision. It's very difficult to deal with clutter, objects that are stacked. So the robot scans the room, figures out where all the objects are, figures out a plan of how to sort that, tidy that room. Then it translates that into a game, a social game with the children. And the children start playing that game with the robot. At the same time, the robot is analyzing the way that they play together, whether they are playing nicely together or not. Maybe there's a child left out, and it'll adapt the game to pull that child back in to keep them all involved. It sounds simple. It's quite challenging. Here are some of the steps, some of the experiments and steps and studies that we did to inform that. So this is a Squirrel Robot that we ended up with. It's quite large. That is the pain of making robots. They have to be so large right now. But basically, we first observed children and identified when there was a conflict or not. That we tried to do feature modeling to figure out if we could detect conflict between multiple users. Translate that to a robot and train it so that it starts to detect engagement, detect conflict, and their behaviors. Same with full body features. And really, these are all aspects of robotics that normally work isolated from each other. And when you put them together, you have to try and make more than a combination of that. Something new has to emerge. I think that is science. Something new has to emerge from that combination of vision, for instance, skeleton tracking, but also planning and navigating and the psychology of the movements of the robots, etc. A lot of studies to investigate how the interaction could be best designed. Very complex handover between a human and a robot. There are so many questions we have to solve before we can develop an AI solution. We took the children along in a co-design method throughout the development of this robot, which meant we need to develop new methods of evaluating, where psychologists and designers were very eager to find out more about how to do that. And then we deployed longitudinal case studies. Yes, please. Exactly, yeah. This is online. It detects online and responds to it online. The challenge is to address the child. So stuff is happening there. These two are beating each other. That one's left out. You look at that one, those guys are still going. It's basically any parent has that problem, but the robot was really struggling with that. The challenge is really, normally I think we designed for a one-on-one interaction, but now it's time that we start looking at multiple users interaction. That's the challenge of this study. Does it answer your question? Okay, thanks. I tend to veer off in a different direction. Okay. How am I doing on time? I feel like I'm walking into it a bit. Okay. Let me give you a last example. Then I'll skip a few things and I'll explain to you a bit more about methodology that you might want to think about. This project is a project in a robot supporting children with autism. So very young children with severe autism often do not have the ability to speak or hear a language. And it is very difficult for them to decipher our behavior, to understand the movements of our faces, for instance, and what our behaviors mean. They might see an eyebrow move and then they don't see the whole thing. Basically, they have the same problem a computer has to process our behaviors. For them to be able to participate in society, unfortunately, we are not very forgiving to people that have a different way of processing information. So we need them, especially when they become adults, to be able to kind of respond normatively in a situation. So they receive therapy often, or they receive extra education from their teachers. And the teachers struggle because their body is the way to deliver the information, but the children cannot read that body. So what we found is that when you put a robot in between as the mediator between the child and the therapist, it's very effective in giving that information because we can control the behavior of the robot completely, and we can slowly increase features so that the child learns to understand the facial expressions of the robot. And why I like this as an example so much is because you will have also heard this. People are a little scared of artificial intelligence and robotics. They worry that it might take over their jobs, for instance. And here these therapists are saying it has really enriched my job because now I can mean something to these children that I could never do anything for before. I think if we could use this technology to enrich people, to allow them to be better, smarter, have more reach in their profession, that would be really wonderful. I'm going to skip a little bit, so it's in the interest of time. We run this study in many different countries because the way that people deal with autism is very different in different cultural backgrounds. This is Serbia in Eastern Europe. And I want to show you that this child, it's just one example, but this child cannot deal with people. You can see how he's blocking the therapist from view. But see how he responds to the robot. And his parents were standing with me in the room. There's a mirrored window in the room. And they said that was the first time I saw him smile at something. We didn't know that. We thought, he's always like that, because a couple of times we saw him, he was always like that. So we get a very emotional feedback. And this is not a challenge. I think of when you work with technology that strongly impacts society. Parents want this solution, and they want it today, but they cannot have it today. It's a long time from when we develop concepts and test them and prove them until they land into society. So what can we do to speed up that process? It would be very interesting if we can play a role in that and think about that more together. I put this one in because it's about aging technology. I'm going to run into time, though, but I want to show it. So this is also in French. Yeah, in France, people retire when they're about 50 now. And then they hang out in philosophy cafes, which is wonderful. No, I'm joking, I'm exaggerating. But there are many people, as we go through lifelong learning and we have aging society, we have to rethink the way that we learn and work and socialize. Maybe not all learning is at the beginning and all working is at the end. Maybe and then there's resting. Maybe we need to move in and out of these things. So that means you might not be able to be at work or be at your social event, but you need to be there. So there are obviously many reasons to like telepresence. For instance, we shouldn't go to Mars. I know it sounds exciting, but really, can we just not send a robot, log in the morning, and come home for dinner? I mean, it makes much more sense to me. So telepresence is obviously something very interesting. And in an entire lifespan, having the ability to be somewhere telepresent through a robot might be very helpful. This was figuring out how can we develop a telepresence robot to support elderly that might have to recover and cannot join their work or life activities. So we wanted a robot that would take away the low-level functions. So you don't have to worry about driving around with the joystick. The robot does all that. And you can focus on the interaction. So this robot, for instance, detects whether someone cannot hear you and adjusts volume and leans forward. It keeps a proper distance when you walk along the corridor together. And takes all those features, but there's also like an interesting master-slave relationship we have to figure out, which function the telepresence robot takes over from us and where we want to take it. And of course, this feeds into the autonomous car research a lot. Okay, I wanted to leave you with 2 examples. When I speak to industry, often they say, look, we want to know what's going to happen with artificial intelligence. It's so expensive, to figure out that research, to find out what it will do. And I wanted to explain to you that it doesn't have to be expensive. You can be very creative about investigating the future. And I wanted to give you a few examples. And first I want to sketch the problem. Here's a driverless car. We're seeing it from the point of view of the driverless car. This is in collaboration with Stanford, so this is somewhere in Palo Alto or Menlo Park. And here you can see how people respond to a driverless car. It's difficult to design the behavior of a driverless car because people respond so differently. This person's like, hey, a driverless car. I'm not going. Well, maybe I am. No, I'm not. The lady on the other side, on the hands, she doesn't see it or she doesn't care. So how can a car communicate? I'm going to drive or I'm going to stop for you. You can go first. And we need to figure that out. To figure that out, it might be very expensive. Also, we are all restricted by regulations. I'm not allowed to put an autonomous car on the road with my own algorithms. So I have to be very creative. And I wanted to show you how you can do that. Lost my cursor. Show you how you can do that. So let me pull this forward a bit. So what we did was we made an autonomous car. It's, I am not breaking any rule, but it allows me to investigate how people respond to driverless car behavior. So this is a psychological experiment to inform artificial intelligence design. It looks exactly like a driverless car. We can run the experiment, figure out, have the machine learning systems running on the data that this car collects, and improve our algorithms as we go, as they respond to the different behaviors that the driver shows. To inform development of new cars. Here's another example. Okay, I could go on forever. I'm worried about the time. Here's another example that I will show you.
Does this feel like kind of okay?
Let me explain it to you first. It needs a little bit of introduction. Once you sit in a car that is autonomous, you get to say nothing. Right? The car is going to drive. There's cars coming from all kinds of roads, and your car is going to brake for you. Well, that's really nice, but we want to know how passengers in the car respond to that. Again, I am not allowed to put a car on the road with particular algorithms, so we have to investigate it. So what we did, and this is a very early version, I couldn't get a nice video together of the later prototype. I'm sorry about that. They're working on it now, the students. It basically creates a virtual reality environment in a moving vehicle. So you sit in the vehicle, there is a driver, you don't know about that. Well, this is a prototype version, but in the real version, you don't know about that. You have a steer in front of you, and all your input comes through the virtual reality. So it's very compelling. Also, you don't get so sick because the motions are aligned with the real motions in the world. Okay, so let me show you how that went for this person.
Does it feel like I'm in a car? Yeah.
They might use
can you put your hands out
an expletive word. I'm not exactly sure.
Right.
Just to warn you.
And just leave them kind of center in your vision. And now you can just, if you drive straight, you should be going just...
Yeah, so he sees his own hand. This is kind of what he sees, this rudimentary video of the early version of it. The only input that he gets is really from this, right? This is what he sees as he's driving. Oh, there's a car coming, a white car. Oh my goodness.
God. It just...
It feels very real.
It was funny. Like there was a car hitting them in VR.
These kind of tricks help us to very rapidly get data and get information to train our algorithms. Okay. I wanted to finish by showing you something I'm currently working on, the latest. It doesn't look so great, and I need to explain it. So before I show you this, I will explain it. The idea is that you can collaborate together at a distance. For instance, maybe we decide to start a collaboration together, but we need to build it together physically. So we need to put, I don't know, blocks on top of each other, you and me. So you have a robot here, and I log into your robot. And together we start building this with our hands. That means that I am at the other side of the world, and I have to feel like I'm totally immersed there with you, see everything that you do, see my own robot hands, and know what to do. Also, there is a time difference. So the technology has to kind of predict what will happen to reduce the time difference. So we have to build kind of a time machine as well. Also, you, on your side, have to communicate with me. And you have the robot there. So you need augmented reality to know that I am there. Okay, here's the setup of the first sample of that. I promise you then I will stop. I realize this is a long talk. Okay, let me turn the sound on.
Hey, hoi.
Hey.
Waar moet ik naartoe met mijn hoofd? Where should I go with my head?
Okay, so the first laser beam is here.
So they are remote.
It's a vertical one.
They are in the same room together.
And so
the person that is remote can see where the laser beams are.
But there's one here.
In the room with the laser
so if you have your
cannot
head
see them.
around
so needs
here,
help from
it's
the remote
fine.
person. This is
You
not
can
with the
come
robot
closer,
setting.
but you have to watch out because there's one over here.
Hands.
Okay.
So you should
She
keep
is
kind of low,
here.
but higher than this. All right. Now you can come.
You would see me as if I am these arms.
And a bit to the right.
And I would see you as
Yes.
there.
Closer, closer. And then a bit closer. And you can stand up again. All right. Let me check the following one, because there's one here. It's a diagonal one.
The next step is I want to place
so
a robot there. This is the virtual version.
For you, you can go down
there is
here.
Actual interaction possible.
If you
Seamlessly.
Yes,
and
great.
It feels
And now
like we are
come
really
here.
together.
Yes. Yeah. That's awesome. You're already there. Nice. Good job.
All right.
High five.
Thanks.
Okay, this goes on. Last comment. I promised to come back to ethics. I want to show you this child who is working together with a robot. And of course, we see many of these aspects. Robots coming into our lives, interacting with children, and it raises many questions. It raises many questions about how these children will relate to others as they grow up. How will they relate to robotic technology in their environment? And these questions are raised constantly, and we really need to address them together across the humanities, across engineering. And I really hope to have piqued your interest for this. Thank you.
Okay, I remember there's a top AI scientist who is the most cited AI researcher, Professor Nick Dennis, predicted in the future our world will become human being and AI being collective. So no matter we are willing to or not, like in our daily life, we will be interacting with various of the, like either virtual agent or real robotics in the world. So today we have a very impressive talk in the social AI, and there are time for a few questions. So yeah.
Thank you for an excellent talk. I don't think I just wanted to know, I have particular research interests, which I won't go into.
Okay.
But, so this is going to seem like a strange question, but how do you, the researcher, and the robot filter out deviant behavior? If they're learning from a social environment, then all you have to do is introduce the bloke at the airport who sits right next to them. and that's inappropriate. So how do we make that not a part of their learning? And what are the ethical considerations for deciding who's deviant?
Well, in all these research projects, we work closely together with philosophers and ethicists. And they often what happens is, even before we begin, they design kind of a framework for investigating this research. And they, very early, they present that to us. They say, okay, these are the questions that we think will come up and that we want to address. It might be, for instance, what if deviant behavior is learned by a machine learning system? Because it's possible, and you hear it all the time. There was this Facebook chatterbots or something, and they started saying horrible things because people were teaching them horrible things. So this can happen, and we can only take one or two of such topics, and then deal with the technology around that. And the solution might be very different. It might be that we make them moral machines with restrictions and rules, that we say, okay, there's some semantics that we need to add in here. Sometimes we need to take on board an extra partner to be able to deal with that. For instance, if it turns out that the content of natural language is really important because of this deviant, then we might turn out and say, well, we didn't have a natural language expert in our team, but we need it now to be able to solve that problem. So I have to say we deal with it very practically at a case-to-case basis, which my philosophy partners would bring up. Does that answer your question, though?
Absolutely.
Okay.
If I may just ask for clarification then, what kind of disasters have you had?
Oh God, where to start? No, of course there are so many, but sometimes it's hard to start, just to choose where to start. To give an example, I hope that's appropriate, is for KLM Airport, for instance, they said, look, many Chinese people are starting to travel. From Chinese mainland, people are starting to travel. They're not used to traveling. We want to support them and help them when they arrive in our airport. So can you recognize Chinese people? And I was like, I can't put my finger on it, but it just doesn't feel right. So like, I'm going to come back to you about this. And there, I also found it so helpful, so supportive to go back to my colleagues in humanities to be able to wrap our heads around kind of this question, which is obviously something that they need to provide a proper service, but may not be something that we would want to engage in to develop.
Any more questions?
I have a question about social referencing,
yes,
which sounds great to me, but I don't know if I really understand it, because you talk a lot about observing. You know, you get people to do all kinds of things, so the AI, the machine learning, the robot can observe and learn from it. But as we know from studies of human learning, of course observation comes into it, but most of it is through action, not through observation.
Absolutely.
Or observation in action.
Yeah.
So how do you can you incorporate that into the AI learning so that it actually learns as it does things?
That's a fair point. When I said observation, I didn't mean to restrict it to vision. So you can, maybe I should have called it experience, because indeed you can experience solely through touch. And actually, I didn't show it here, but there's one experiment that we are doing with people that are paraplegic to allow them to feel their body again. So we translate touch behaviors that other people might stroke them and move these behaviors to an element in their body where they can still have feeling. So you are addressing a very good point. It's indeed all the senses that help you learn. But the main point I want to make is that it is social. It's social in nature because it's other people giving us those cues. And they can, of course, be any modality.
And interactional, I suppose. Yeah.
Interactional cues.
Yeah, so do you have an expert in human-human interaction on your team?
Not in my team exactly. I have psychologists in my team, and I would say they are human experts, but like a real deep understanding of how people feel, how people behave is really important. So I have 3 psychologists in my group, and it's in a computer science department. It's quite challenging because I have to consider a career that I can offer them. I have to also convince my computer science department that this is the way to go forward. So I think this is why, for instance, cross-disciplinary institutes are so important to be able to get these people together. But for sure, human experts. I want to give one caveat, though, and that is that I have found that often we have made the mistake to put the human as the end goal, where we say, okay, if we do it like humans do it, then we're right. And sometimes that's not the case. Sometimes there's another way that's better, inspired by biology or others.
Thank you. Very engaging talk indeed. Thank you very much. One thing which you didn't really address so much was the limitation and the way forward. Are we limited by our imagination, by the development of algorithm, or by the hardware? What are the stumbling blocks?
Very good question. I'm glad you brought it up so that I can stick it in this conversation. There are a couple of things that I am waiting for that would really help. One of them is, of course, energy. It's not efficient at all to build a robot. You put a cookie in a person, they run the whole day. But what about a robot? It takes so much energy to have a robot. So often it's not the environmentally right option to go with a robot. So if there is a new way to transport energy, maybe through fluid, like the human body does that with blood, that would be really interesting. And that kind of a solution is needed, an answer to batteries, something like that. Another is natural language. Even though natural language has come surprisingly suddenly again a long way, it's very restricted to the world in which it is supposed to operate. You can buy stuff and have a reasonable conversation, but as soon as you talk about something else, it starts to break down. And it doesn't seem to be a solution very soon to that. So that's another big one. Hardware, a little bit related to energy. So I'm very restricted because of hardware. You need all these different systems to run. Sometimes you end up with a robot with 4 laptops in it. That's ridiculous. You have to be free from the body to be able to design the exact body that you need for the job. And that's not possible at the moment. So there are many restrictions. And then, there are many regulations that we need to figure out, or the lack of regulation, which is really difficult. You might say, look, I want a car to do this, but there is no regulation around it, so I don't know what to put in it. Should it brake for a deer or not? And that's also restrictive in a way. So.
Okay, I saw this. Another question.
Thank you for the talk. Let me just get it right. In the beginning, you said animals do not have a social referencing?
Chimpanzees don't tend to engage in social referencing, definitely not as much as humans.
Because I don't know whether you watched a particular YouTube talk about a small monkey in Japan where they serve and behave like a waitress.
Yes.
So how would you then, because that to me is quite important because that seems to be where you start the whole thing from. So I would like to hear your comment on that.
Fair question. Very fair question. Let me try to address that. And also, I am very aware of my own limitations. There might be a monkey species out there that is amazing that I don't know about. So let me start with that. I would guess that this monkey is highly trained. And it has probably been trained through reward and punishment, which is different in a way than we are trained. Although you could argue, when mother smiles, it's a reward. And so in a way, we are trained in that way. Social referencing is really, for the example of the chimpanzee group with the stone and the rock and the nut, would really mean like, hold this, and then the baby holds it, you go, yes, you're holding it. It's active teaching and social referencing at the same time. And that is something that Tetsuya Mosuzawa, my collaborator, says he does not observe in the chimpanzee groups that he observes. Is that sufficient an answer for your question? I'm happy to address it in more detail.
Yeah. Okay. Yeah. I think we have many questions from professors already, and the food is waiting outside. But Professor Vanessa, I was yesterday expressed she really want to interact with students. So maybe we open the last question to student, and later you can continue the communication. But remember to keep a right distance. Okay.
I set up expectation.
Yeah. So any question from our student? You are our student?
Not really.
Yeah.
Very shy student. Oh, there's a student in the front there. Right, yeah, or two.
Yeah. Okay. So, please. Yeah. Okay.
You mentioned earlier a robot that was able to recognize engagement and conflict.
Right.
How did you choose the features?
Oh, they were features that were trained. So first we observed children playing, and out of that we realized playing with objects. Out of that we realized conflict and engagement were the most salient, interesting features for us to manipulate the game. So it is a contextual analysis done through a psychological method that gave us that inspiration. Am I hitting your question?
I was just wondering what precisely led a computer to think it was a conflict.
Oh, right. Well, what we then did was we said, okay, we are interested in conflict. So then we collected a lot of examples of conflict in children, a lot of examples in engagement, and we fed the computer all these examples. And it started to extract features that predicted a conflict. For instance, raising the voice, certain body movements. So yeah, these are features that you cannot predict yourself, but the machine learning system will find them as most similar in all those examples. Yes.
Okay. So let's thank Professor Vanessa. Oh yeah. So we finally got one student. Okay.
Okay, so you said that you sometimes use children to get a design thinking for the robot, right?
Yes, to engage, to take them along in the design.
No, I mean to get along with the design. Like, is there any difference between using a children and using adult to create a robot in terms of behavior, of the robot behavior?
Yeah, children are much smarter in the sense that you can't fool them. You know, I think what happens when adults are exposed to a robot, they say, well, you know, it might work like this, and it might maybe that's happening. But children, they see what they see, and and often they are just right. Yeah? If you ask a child, what can this robot do? It's because you programmed it. Whereas a person is thinking more complicated, adults thinking more complicated, and then I find there are many differences. Maybe one interesting twist to an answer to your question is that this research with the children, it's financed by a very large software company in India. They are interested to know how their teams work together and whether they are creative and collaborate well. So we started studying with their people, but the things we found, they weren't taking on board. They weren't listening to it. They thought, no, that's not true, that doesn't happen. Then we replicated that with children, and we showed them the results we had from children and said, oh, that happens in our teams too. So there was something that helped in having children show aspects of human behavior that made the company accept the results.
Oh, okay. Fantastic. Thank you.
Okay, yeah. So thank you all, and let's put our hand again. Professor Vanessa.